Okay, we're going to start off talking about the probability of two independent events. And I'll get into what independent events mean here in a second. But just for an example, let's do this one. So it says, suppose we flipped a coin and rolled a die, and we want to know the probability of getting a head on the coin and a 6 on the die. So what we could do is you could list them all out, right? Where you've got a head and a 1, right? That's like one thing that could happen, a head and a 1. Or this one is like a tails and a 2. But in total, there's 12 of them, right? And there's only one desired outcome here. So this is just from before with probability. We can say, okay, well, we wanted a head and a 6. Well, that's this one, right? So getting a head and a 6, there's only one of those. So that would just be one outcome out of a total of my 12 possible, right? Okay, so this is an example of an independent event. And it's independent because, well, here, I'll read the definition first. Events A and B are independent events if the probability of event B occurring is the same whether or not event A occurs. Okay, so I know that sounded a little bit confusing, but all that meant, like in our last example here, was that we were flipping a coin and rolling a die. So what they mean there is the flipping of the coin didn't affect the rolling of the die at all, right? It didn't have any outcome on whether or not the die came up 3 or whether the die came up 5. Right? So they're independent of each other. They don't affect each other, right? It's pretty, like, I don't find that a very tough concept, but you guys are going to see this word independent event quite often. And then you probably see what's coming in the next video. I'm going to talk about dependent events where the first one actually affects the outcome of the other, okay? So are these events independent? So it says a fair coin. So you'll see that before we get going. A fair coin would just be a coin that's like it sounds. It's fair, right? It's one that doesn't have, like, two heads like heads on both sides of it or something like that, right? Anyway, so a fair coin is tossed 2 times. The 2 events are first toss is heads and second toss is a head. So are these independent events? Well, yeah, because flipping the coin the first time, right, didn't have any effect on flipping the coin the next time, right? So the next one here says the 2 events. So the first one is it will rain tomorrow in Houston, and the second one is it will rain tomorrow in Galveston, a city near Houston. Okay, so are those independent? Well, not really, because especially since they're near each other, if it rains in one place, it's likely to rain in the other place. So they're not independent. They're kind of tied together, right? They're not on their own. Now, it would probably be if it was, going to rain tomorrow in Houston, and then it was going to rain tomorrow in Paris, right? Those would probably be considered independent because they're so far away, right? That they don't really have any effect on each other. Okay, and then C says you draw a card from a deck, then draw a second card without replacing the first. Okay, so you had 52 cards. You took one of those cards out, and then you drew again. Well, if you think about it, when you drew again, how many cards were there? There was only 51, right? Because you took one of the cards out the first time. That changed our probability, right? So that's going to be our dependent events. We're going to do some of those later on, but for now, yeah, we can see that this is not an independent event. Because the first one affected the other, right? All right, keeping on going. Okay, so when 2 events are independent, the probability of both occurring is the product of the probabilities of the individual events. All right, again, that sounded confusing, but and here, maybe I'll confuse you a little bit more. Let's go through the math jargon here. So it says, if events A and B are independent, okay, so A and B, then the probability of both A and B occurring is, and then we have our little formula, probability of A and B is equal to probability of A times probability of B. Okay? Now, this formula actually is on your formula sheet as well, but it's written a little different, and it's because, from our last unit there with set notation, it uses a little bit of set notation. This one's saying probability of A intersection B, which is and, right? So if this is why I brought our picture back up again. probability of A and B is the area of overlap is kind of a good way to think about that, right? And yeah, so the way we can find this is actually just by multiplying them. And like I said, there's a bunch of math jargon here, and like this sounds like a confusing statement, but I'll show you in a second why it's not. Like if we do an example, all it really means is if I want to figure out the probability of A and probability B happening, all I have to do is multiply them, multiply the probabilities. So if there was a probability of, let's say, 25% or 0.25 of A happening, and let's say 30% of probability B happening, I would just go 0.25 times 0.3. And there you go. That, like, just multiply those together, and that's the probability of both of those happening. One thing to notice when we're multiplying probabilities, right? you might have a funny reaction to this, where you might say, okay, nope, wrong way. Probability of A intersection B, where you might say, okay, well, if I multiply those numbers, isn't that going to make it more likely that they happen? But no, they won't, because remember, when you multiply decimals or numbers that are less than 1, greater than 0 but less than 1, the numbers actually get smaller, right? So when you multiply these together, we're going to get a smaller percentage out of that. Here, let's actually, just for example here, let's do that. So we're going to get 0.25 times 0.3, we get 0.075, which is like 7.5%, right? So the probability of both of those things happening together ends up being a smaller probability, which is what you would expect, right? Let's do some examples though. So it says, if you draw in your drawer you have 10 pairs of socks, 6 of which are white, 7 t-shirts, 3 of which are white. If you randomly reach in and pull out a pair of socks and a t-shirt, what is the probability that both are white? Okay, so the probability of choosing a white pair of socks is 6 out of 10, right? There was 6 white ones in there. There was 10 in total, so we just say, okay, probability of that, 6 out of 10. Okay, the probability of choosing a white t-shirt is, okay, well, you got 3 that are white of the 7, so that's 3 of the 7. Now remember, these really could be written as decimals as well, right? And so you could do that, you could change them decimals first if you want to, or just leave them like this. But then the probability of both of these things, these two independent events, because one didn't affect the other either, right? Like when I reached in, I was gonna grab, some socks, I was gonna grab a t-shirt. Grabbing the socks didn't affect how the t-shirts came out, right? So those are independent. And if I multiply them, then we just get 18 over 70. 18 over 70, which would simplify to 9 over 35. So there's our new probability of both of those things occurring. And again, here, just so we get used to it, let's go 9 divided by 35. Nope. 9 divided by 35, and we get 0.257. So that would be the same thing as 25.7%, right? So a 25.7% chance that I am going to grab white socks and a white shirt. Okay? Just multiply them together. That's all we got to do. Okay, so I'm going to skip through that one. Let's go example 9. So I'm going to move through example 9. This is kind of just getting us into OR probabilities. But I'm going to jump right into it. So now what we're dealing with, so the last one, remember, was probability of probability of A and B. So the probability of, getting white socks and white shirts, right? So and probability. Now what we're going to be doing is OR. So the probability of getting white socks or white shirts, right? So this is like one or the other. Now, again, the OR statement, I'll kind of show you the picture again. You can think of it this way. Or, like if this is probability A and this is probability B, OR would be either or. It's the whole thing. It's the union of them, right? It's the union of the two. So, if we want to find the probability of OR, we have a formula for that. So the probability of P or B, or probability of A or B, I mean, then we could also write that as the probability of A union B, which is just the probability of A, right? The probability of A, that one, the whole circle, plus the probability of B, so that whole circle. Okay, so those two added together. And then what's going on here? Well, then what we're doing is we're just subtracting out the middle, right? We're just subtracting out the middle part, right? Because remember, we did this formula in set notation, where the reason why we're subtracting out the middle is because if I just added up A and then added up B, you can see that what we did is we actually ended up like counting that middle section twice, right? We counted for it once when we did the A, it counted for that. But then when we added the B, we like added that section again. So we just need to subtract that section off. And then when we do that, we end up just getting the union, right? Everything else, so that's left there. And for the most part, you guys probably won't need to like think about it using this equation. You might need to, though. Maybe the question's kind of worded in such a way where they use these symbols and everything. But a lot of times when we do these probabilities, we can think about it a lot more intuitively, I think, than that, or maybe a bit more in a common sense approach. But yeah, I'll show you as we go here. So this one again is on your formula sheet too. That one there. Okay, so now it says, suppose we draw one card from a standard deck. What is the probability that we get a queen or a king? Okay, so let's just think this one through. There are 4 queens and 4 kings in the deck, right? So there's going to be 8 different outcomes that are going to correspond for that. So then in our example, it's really just going to be 8 over 52. And then really we could simplify that, right? But I'll just leave it for that for the time being. Now let's look at our equation though, right? So the equation from above was, here I'll do the whole thing. Probability of, here I'll do in king union queen, right? Just or is what that's saying, right? King or queen, or union, is equal to probability of the king plus probability of the queen. And then we subtracted the probability of the king, sorry, don't write it out, just K, and then intersection queen, which is king and queen, right? That's subtracting out the middle, right? That last part, just again, I keep saying this, but that's just subtracting out the middle section right there, okay? And if we do that, it actually ends up working out because we ended up with, in this case, all right, there were 4 queens, so that would be the probability of 4 over 52. There were 4 kings, so that would be, sorry, other way around. There was 4 kings was the first one, and then 4 queens, so the probability of 4 out of 52. And then minus, okay, well that last part was 0 because there is no overlap, right? There's no overlap at all between those. So it still ends up being 8 over 52, right? It was probably easier in this one just to do this in our heads, but the equation did hold true. Okay, so it ended up being the same. Now, in that example, what this is called is a mutually exclusive event. Okay, I know that sounds like a big word, but mutually exclusive, I think it kind of makes sense when you say it. So if it's mutually exclusive, it's kind of like saying both of these are on their own. They're exclusive. They're doing their own thing, right? So mutually exclusive. They don't care about each other, right? You can just add them up. Okay? So yeah, so now our mutually exclusive, you can think about this as like a new formula if you like, but really it's the formula from above, but we just subtract off the overlap. And the reason why that is because, well, you can think about our two Venn diagrams from above, right? Let's look at our Venn diagram from up here. Imagine circle A just moving to the left and circle B moving to the right. Then there is no area of overlap, right? They don't overlap at all. So then the equation would just become, okay, we'll just add up the probability of A with the probability of B and done. Okay? All right, let's move on. Well, let's do this one because it shows a good example of where it's not mutually exclusive. So it says, suppose we draw one card from a standard deck. What is the probability that we get a red card or a king? Now notice the difference between this and the last question. A red card or a king? Well, there are some kings that are red, aren't there? So we're going to have to take in that area of overlap. We're going to have to take in like where they overlap, right? So let's do this. We'll say, okay, half the cards are red. So 26 out of 52, right? So that would be the probability of getting a red card. Okay, there are 4 kings. So that would be the probability of the kings, right? 4 over 52. Now, there are 2 red kings. That's the overlap, right? So if these were my 2 circles, then so far what we found here is that this circle, if this was my red cards and these were my kings, then the red cards would be 26 out of 52, I guess. We should do the whole thing. So 26 out of 52, right? That would be that probability for the whole thing, the big circle. Okay? And then there are 4 kings, so that would be this one. There's 4 kings would be the whole thing. And then the next part would be, okay, well then actually 2 of those are the area of overlap. Sorry, I should go over 52. That should be like 2 over 52 because we're doing probabilities, and 4 over 52. Okay? But really, sorry to be confusing, I can do 26 over 52 and treat these like probabilities, but maybe like an intuitive way of doing this too is you probably could just write in like 26 because we know what the total is. And this could be 2 and this could be 4. Right? You could do it that way too and just leave it with simple numbers like that. And then just know that our universal set is 52 cards, right? And then we can like do it afterward. Either way though, in my example, we're just saying, okay, the probability of getting a red card is 26 over 52. Probability of a king, 4 over 52. And then subtracting the middle, we get 28 over 52. Okay, so that's one way of doing it. The other way of doing it, which I know some people might do it this way instead, I think I might do it this way instead sometimes for sure, is let's actually just figure out what the union of these 2 circles is. So if we're just looking at cards themselves, right? So we'll say, okay, well right now this 26 was for that whole circle, right? That was all the reds. Let's actually just figure out what just red would be. Okay, well that would just be 26 minus the overlap. That would be 24. Okay, so that'd be 24. And then this side, well, if the whole thing is 4 in the middle, then that would be 2. Okay, so now from that we can figure out what the union is. So that would be 24 plus 2 is 26, plus 2 is 28. So that would just be 28 over 52. Just the union, right? All of the union over my total of 52. Okay, so I'm going to let you guys choose which way you want to do it. All right, moving on. All right, so let's look at one of these table examples. So it says, the table below shows the number of survey subjects who have received and not received a speeding ticket in the last year and the color of their car. Find the probability that a randomly chosen person, A, has a red car and got a speeding ticket, and then B, has a red car or got a speeding ticket. All right, so for the first part here, it's just so red car and got a speeding ticket. Well, then if we look at this row, these are all the red cars, right? So this is red car, and then this is the red cars that got a speeding ticket. This is red cars, no speeding ticket. And then the total just of those 2, that's really just going to be like that one and that one added together, right? And then not a red car, and then here's the number of speeding tickets, no speeding tickets, and then add those 2 added together. And then your total for speeding tickets would be 60. Total for no speeding tickets would be 605. And then just your total, like your entire total, is this one, right? All right, so in this case, it says we can see that 15 people, all right, so just these 15 had both a red car and got a speeding ticket, right? That's where they intersect there. So that's really just 15 over the total, right? The total of people surveyed was 665. And that's it. So that'd be your and one. Okay. And then your or probability. Okay, so your or probability, looking at this table. Here, I'm going to do it over on the side here just so we can kind of see the table at the same time. Well, I know again that my total is going to be 665. But the question is, what's my numerator going to be? What's the top going to be in this probability? Well, okay, we just need or. So, okay, has a red car or got a speeding ticket? Okay, well, that's a red car. That's a red car. Even though, like, because I'm looking at just red cars in general. Well, both of those numbers are red cars. So we can just add those two together. And then not a red car, but got a speeding ticket is that one, right? So we got to add just really those three numbers together. Okay, and if you do that, you'd end up getting, that would be 195. Yep, 195, right? And that's it, right? So we're just saying or. So red car, so that's a red car, that's a red car. And then this one's not a red car, but it did get a speeding ticket. This one doesn't count, right? Because that's not a red car and it didn't get a speeding ticket. So that doesn't fall into our probability there.